So this is the 37th lecture of this course, 37th lecture, and today I'll discuss some very basic problems with you. So first problem is this. What's the problem? It says determine the built-in potential of a silicon PN junction diode. First of all, you have to find the built-in potential. This is asked. You have to find this built-in potential of a silicon PN junction if it is doped by a donor impurity. If it is doped by a donor impurity at the rate of this much, 10 to the power 17 per centimeter cube, and by acceptor impurity at a rate of 10 to the power 16 per meter cube, and given that the intrinsic concentration of silicon is this much. So what is given to you? First of all, donor impurity, that is Nd. It is given. Look at the solution. This is the solution. Nd is 10 to the power 17 per meter cube, and acceptor impurity 10 to the power 16 per meter cube. This Na is 10 to the power 16 per meter cube, which is given to you. Given that the intrinsic concentration at the same time Ni is given to you. This Ni, intrinsic concentration represented by Ni, it is 1.5 into 10 to the power 10 per centimeter cube. Now determine the built-in potential. You have to find the built-in potential. I told you that what is built-in potential or the barrier potential. Either is a built-in potential or barrier potential or contact potential. One is the same thing. It is nothing but simply when a semiconductor, a PN junction, is formed by doping a semiconductor with some donor impurity as well as with the acceptor impurity, and near the junction a potential is formed here, that is called the built-in potential, either V0 or VT, whatever it is, or VB in some of the books. VB, built-in potential, VC, cut-in potential, all these are same. You have to find this potential here. It is asked, determine the built-in potential in a silicon PN junction if it is doped by donor impurity. This is given to you, and acceptor, of course, intrinsic concentration is given to you. Now I told you that this built-in potential V0 is given by Kt upon Q into log base E of Na into Nd upon Ni square. All you have to do is simply apply the formula. But remember, or I can say I represent this as Kt upon Q. Many times this, mostly this log base E is also written down as Ln of Na Nd upon Ni square. This log E, log means log base E. Remember that this is the natural log, not the common log. This is not base 10. So be very careful while doing the calculation. With the help of calculator, press this button of Ln, not log. So this is the only point why I have done this problem with you. So it will be equal to, I apply the formula here. It is, you have this built-in potential V0 is equal to Kt upon Q into Ln. Ln means log base E. Ln means this log base E into Na Nd into Nd upon Ni square, and I leave this as a calculation for you. This much volts, whatever you get, will be a final answer. I leave this as an exercise for you. Now, one more thing, determine the built-in potential of a silicon PN junction diode. Now see, since the temperature is not given, so I assume it at room temperature. I am writing here, but if it is not given, you assume it as room temperature. If temperature is given to you in Kelvin, it's fine. Otherwise, assume this as a room temperature, and you just simply find this, the built-in potential in volts, whatever you obtain. So this is the first problem. Second problem. find the diffusion coefficients of electron. You have to find the diffusion coefficients, next problem, of electron and hole of a silicon crystal at 27 degrees centigrade. Now here the temperature is given to you. Of course, when I say temperature in 27 degrees centigrade, then this temperature in Kelvin will be 273 plus 27, and I can say that this is equal to 300 Kelvin, of course. Now it is room temperature by default. So find the diffusion coefficients of electron and hole of a silicon crystal at this much if the electron and hole mobilities are given to you. This is 0.17 meter square per volt second and 0.025 meter square per volt second respectively. Electron and hole means this is mu n, it's given you that this is mu n. Mu n is 0.17 meter square per volt second, and of course this whole mobility mu p is given to you 0.025, same unit, meter square per volt second. Let's write it, meter square per volt second. This is given to you, and it has been asked to find the diffusion coefficients. Now what is this diffusion coefficients? Let's recall it. I told you that Einstein relationship says that dn upon mu n is equal to dp upon mu p is equal to kt upon q. Of course, k is Boltzmann constant 1.23 and 1.38 or 28 into 10 to the power minus 23 joule per Kelvin. T is the temperature. Q is 1.6 10 to the power minus 19 coulomb. This is the Einstein relations that I discussed with you. So from here, it is a very simple problem. You have to find this diffusion constant. It says determine the diffusion coefficients of electrons and holes. This is the diffusion constant of hole and this is the diffusion constant of electron. I hope that this is clear to you. So what I need, if we note that since, look at the solution, since dn upon mu n, of course it is equal to dp upon mu p, dp upon mu p is equal to kt upon q, or from here I can say this implies that I have to find two things here, dn and mu n. What is asked? Diffusion constant of electron and hole. It means I have to find the value of dn and I have to find the value of dp, diffusion coefficients of electron and hole. So dn, so this implies that I can say that dn is equal to mu n into kt upon q, and at the same time this dp is equal to mu p into kt upon q. Now this mu n is given to you. You simply substitute the value of this mu n is equal to this much. This mu n, you simply substitute the value of this mu n is equal to 0.17, and this mu p is equal to this much. K you know, T already we have calculated, it is equal to this much, it is a room temperature, and Q 1.6 10 to the power minus 19, and again I leave this as an exercise for you to find the value of dn or dp, how much meter square per second it is. So I hope that you can find this. Let's move to the next numerical. Just to save the time, I am not doing the calculations. Next problem. Another problem says that an electric field of 10 volt per centimeter, electric field of 10 volt per centimeter is applied across a semiconductor crystal. See what it says, just try to understand. This is a semiconductor crystal here. It's a semiconductor, either germanium or silicon. An electric field of 10 volt per centimeter is applied here. Means after applying some voltage here, an electric field E, which is equal to V by L, volt per centimeter, is applied here, that is 10 volt per centimeter. 10 volt per centimeter is applied here across a semiconductor, and this moves the charge carriers see, this semiconductor will have some charge carriers. It will have electrons and holes. Suppose I am saying I'm talking about electrons only. So it says that this moves the charge carriers at a distance. Naturally, by the application of this electric field, these electrons will drift with certain velocity, or they'll move certain distance and certain times, means they'll drift with certain velocity. It says these charge carriers moves the charge carriers at a distance of 1 centimeter in 20 microsecond. So this L is given to you, how much it has covered, the length or the distance that after the application of this electric field, it has moved. Length is 1 centimeter. 1 centimeter in 20 microseconds. Let's say it is only centimeter, so let's make it in centimeter. Let's make it, convert this in second. This time is equal to 20 into 10 to the power minus 6 second. Determine the mobility. One more thing is given to you, E. This E is 10 volt per centimeter. Since everything is in centimeters, so I'll find the answer in centimeters only. Determine the mobility. The question is asked to find the mobility. Now, if you remember, I told you that on the application, just look at the theory, even if you don't remember the formula. In the theory, I told you that by the application of this electric field, these electrons, they drift with a particular velocity, and that velocity is called drift velocity, which is directly proportional to the applied electric field. And I said that this Vd is equal to mu E from here, and this mobility I have to find here. So from here I can say that this mu is equal to Vd, that is drift velocity, upon E. Of course, E is given to me. Now velocity I don't know, velocity is distance upon time. So I can say this implies that the value of mu will be equal to, this is L upon T. This Vd is distance upon time. It is covering 1 centimeter in 20 microsecond. So the drift velocity of this will be equal to this much into E. And now I substitute the value of this. L is given to you 1 centimeter upon this T is 20 into 10 to the power minus 6 into, this is E is 10 volt per centimeter. So I've done this calculation. This implies that, just cross check this, as per my result it is 5000 centimeter square per volt second. Or if I convert everything in meters, then it will be meter square per volt second. This is the mobility. So I hope that this numerical, very simple numerical, it is clear to you. Let's deal with one more last numerical I'll take, and then I'll wind up with this unit. Let's take it here. I've written the problem here. This is a problem. The problem says, I've done this type of problem with you. A sample of pure germanium has intrinsic charge carrier density. This is the intrinsic charge carrier density. Means Ni. If you see that what is given to me here, this is intrinsic charge concentration Ni. If it is doped with a donor impurity of 1 atom in every 10 to the power 6 germanium atom. Now just try to understand this, that what the problem says, that a sample of pure germanium is here. I'm showing it here. This is a pure germanium here. A pure germanium is here. This germanium sample here. Having intrinsic concentration, the intrinsic concentration of this germanium, this is Ni, is 2.5 into 10 to the power 19 per meter cube. Means it has 2 to the power 5 into the power 19 electrons, as well as 2 to the power 2.5 into 10 to the power 19 holes per meter cube. If it is doped with donor impurity, now it says that this semiconductor is doped with some donor impurity Nd, and of course the resulting semiconductor will be a N-type germanium. Now the resulting semiconductor will be a N-type because it is doped with donor impurity. So the resulting one will be the, now how it is doped? Look at the ratio in which doped with a donor impurity at 1 atom in 10 to the power 6 germanium atom. In 10 to the power 6 germanium atoms, one donor atom is added. First part is this. Determine the majority and minority charge carriers if mu n is this much, mu p is this much, and the germanium density. Look at this now. The germanium density is this much. The germanium density is this much. So I have to find that what is the value of in one atom. Look at this. I'll make a unitary method. Simpler problem. So look at this Nd. It says Nd, and these are the germanium atoms. It is doped with a donor impurity of 1 atom. 1 atom in 10 to the power 6 germanium atoms. In 10 to the power 6 germanium atom, 1 Nd is there. 1 atom of Nd is there. And it says that the density of this is 4.10 to the power 28. So in 4.2 into 10 to the power 28, how many donor atoms will be there? So it is quite simple. 4.2 into 10 to the power 28 upon 10 to the power 6. So I can find that the value of Nd from here, value of Nd will be 4.2 into 10 to the power 22. This much meter cube per meter cube. So I hope this is clear to you. Mu n and mu p is given to you. Determine the majority and minority charge carriers. It says that determine the majority and minority charge carriers. Now, what will be the majority and minority charge carriers? Since it is n type, so it is very clear that electrons are majority and holes are minority. And it is this one. This is n type. Now see, it has been doped by this. Look at the solution here. Up to this point, look at the solution. It is Nd is this much, and this has been made n type. So it is very clear that the majority charge carriers are electrons. So majority carriers will be the electrons. And electrons where? These are the electrons in n type semiconductor. And I told you that these are approximately equal to Nd. So I can say that the majority charge carriers are the electrons in n type semiconductor, and that is equal to 4.2 into 10 to the power 22 per meter cube. Now what are minority charge carriers? The minority charge carriers will be holes. In n type semiconductor, and I told you it is equal to Ni square upon Nd. Ni square upon Nd. So I can say that the holes or the minority charge carriers in this n type semiconductor is equal to 2.5 into 10 to the power 19 whole square upon this Nd is 4.2 into 10 to the power 22. 4.2 into 10 to the power 22. And if you solve this, I have done this calculation, this results comes out to be 1.48 into 10 to the power 16 per meter cube. I want you to cross check this answer, please. Now, I hope that this is clear to you. Find the majority and minority charge. Let's come to the problem again. This we have done. Majority and minority charge carriers. Carrier concentration. If this is given to you, find, next part says find the conductivity and resistivity. Remember that this mu n and mu p is given to you. So I am finding the exact value. The conductivity of a semiconductor is equal to n mu n plus p mu p into E. N mu n means the number of electrons in n type semiconductor and the number of holes in n type semiconductor, which I have already calculated. Just substitute this here. Mu n and mu p is given to you in the problem. Look at this. Mu n is given to you 0.38 mu n is 0.38, of course meter square per volt second, and mu p is 0.18. Simply substitute these values and you will get the value of sigma from here. I am just writing the final answer. I want you to cross check it. From it is equal to 2553.6 per ohm per meter. I hope this is clear. Determine the conductivity, and next is said find the resistivity. Now resistivity is what? I have found the conductivity. This implies that the value of resistivity is 1 upon conductivity. That's all. And if you solve it, you'll get it 3.92, approximately 4 into 10 to the power minus 4 ohm meter. Next part of the problem. If the length of semiconductor is this much, and I'm solving it here only. If the length of semiconductor is this much and the cross-sectional area is this. See what is given to you. Again, given. This is the third part of the problem. Given. The length is 5 millimeter. L is 5 into 10 to the power minus 3 meter. And cross-sectional area is given to you 25 into 10 to the power minus 12 meter square. Minus 12 meter square. Determine the resistance. I know that since R, what is asked? Find the value of resistance R. R is equal to rho L upon A. I have calculated this rho here. L is given to you, A is given to you. Very simple problem, just a formula based problem, and you'll find this, that this R is equal to 78.4 kilo ohm. I want you to cross check these answers please. So I'll stop it here. Thank you for the time being.